Next lecture is the about construction of psychometric chart. So in this lecture, uh, we will study the construction of different property lines like constant DBT lines. So all the vertical line in this chart is the constant DBT line. All vertical straight line are the constant DBT line. Similarly, constant omega and PV line, so these line are all horizontal line, all horizontal straight lines are constant humidity ratio line or constant vapor pressure line. And constant RH line is the curve nature of this curve. This is the RH line. Behavior of RH line is like this: 100% RH line. This is, then there is a 90% RH line, 80% RH line, and 70% RH line. So these are the nature of the relative humidity line. And constant specific volume line, you can see here, this is the 0.80 specific volume line, 0.82, 0.84, 0.86. So these lines are inclined lines. So how we draw these lines in psychometric chart? So this is the objective of today's lecture. Okay, so before going to draw this property line, first we will study how the shape of the psychometric chart is developed. So because uh, basically this psychometric chart, we are indicating the property of moist air, and moist air has a two part: one is the dry air part and other is the water vapor part. And to study the behavior of water vapor, we need to again focus on the phase diagram, that is also called the PT diagram. So this is the phase diagram you can see in the figure. So in the phase diagram there are three type of line. This line is called the solid line, this line is called the fusion line, this is fusion line. And this line is called the sublimation line, yeah, sublimation curve. And this point B is called the triple point for the water is 0.01 degree Celsius. And this line is called the vaporization line, this line B to C. So B2C is our focus. B2C is called the vaporization line because the water vapor present in the atmospheres are vapor, in superheated vapor. So we will focus beyond BC because this is the liquid region, this is the solid region, and this is the gaseous region. So water vapor present in the air are in the gaseous form. So we will focus beyond this vaporization line. Okay, so this is the temperature curve. Here you can see the temperature. This is the 0.01 degree Celsius temperature, which is called the triple point temperature. Again there is a 100 degree Celsius. Again there is a 374 degree Celsius, which is the critical temperature of water. And corresponding pressure at critical temperature is, this pressure is called the critical pressure. The pressure is around 220.089 bar, approximately 221 bar. Similarly, at 100 degrees Celsius, the saturation pressure is 101 kilopascal, 101.3 kilopascal. So in air conditioning purpose, generally the temperature range is up to 50 degrees Celsius. So 50 degrees Celsius line will be at this point, so that will be left toward the 100 degree Celsius line. So 50 will be, this is the 50 degree Celsius 100 line. So generally we work below 50 degree Celsius in air conditioning purpose, and above 0 degree Celsius, 0 degree Celsius. So above 0 degree Celsius, so the psychometric chart, the x-axis will be in between 0 degree Celsius and 50 degree Celsius. So blue color region this blue color region is the basically the region of psychometric chart, because we works between 0 degree Celsius and 50 degree Celsius in air conditioning. We cannot go below 0 degree Celsius, because at below 0 degree Celsius ice formation takes place. Similarly, air conditioning purpose, We generally maintain the temperature in the room is 25 degrees Celsius, and surrounding temperature is generally 45 46 degrees Celsius, so that is below 50 degrees Celsius. So we always work in between 0 degrees Celsius and 50 degrees Celsius. So we will take the corresponding pressure at 0 degrees Celsius, so that is around the triple point pressure. Similarly, the corresponding pressure at 100 degrees Celsius is the 101.31 kilopascal. So 50 degrees Celsius will be, we can calculate from the steam table. So we will work in this blue region. So if we zoom out this blue region, okay, so this part is indicating in the right side of the graph, this, okay. So this part, this 0 degree Celsius is indicating the here, this 0 degree Celsius, and this 50 degree Celsius, this 50 degree Celsius is this point. So we will work in between 0 degree Celsius and 50 degree Celsius, okay. And this is the vertical line, this blue line is vertical line up to B. So this is the vertical line. Now this is the saturation curve, so this is also saturation curve, and we will work, the pressure is far below than the critical pressure, so we will move up to this, okay. So this will be the psychometric chart. We'll work in between 0 degree Celsius and 50 degree Celsius. Similarly, the vapor pressure will be corresponding to this 50 degree Celsius and 0 degree Celsius, okay. So here one question, it is written that this is the figure when no air has been present with water vapor. So this phase diagram is considered only for the water vapor. When water vapor is heated at different temperature, then what is the saturation pressure? So this is the saturation pressure temperature data for pure water. But in air, the water vapor is present, but it is interacted with air. So what is the effect on this figure if air is present? Because in moist air, vapor is present with air, it is not like as a pure water. So if some air, dry air molecule is present with water vapor molecule, so is there any change in pressure temperature data? So answer is given here. Actually, there is a slight interaction between the molecules of air and water vapor, and this interaction is similar as water water interaction. In case of this pure water diagram, the interaction will be pure water water molecule. However, if we take as a moist air, then there will be an interaction of water molecule with dry air molecule, so there will be a very little change in the saturation pressure and temperature data, that we will see in the below table. So a comparison of vapor pressure of water in the air mixture with that of pure water shown in below left table reveals practically no difference in pressure at a given temperature. So here two data is given, one is for pure water vapor, this data is for pure water vapor, and another vapor pressure temperature data is for water vapor present with dry air. So as we can see, the temperature 30 degrees Celsius, the saturation pressure is 4.241 kilopascal, and 90 degrees Celsius saturation pressure is 70.1 kilopascal. So this is for pure water vapor. However, if water vapor is present with dry air, then the partial pressure of water vapor at saturation condition, because it is mixed with air, so here the vapor pressure will be the partial pressure of water vapor, but at saturated condition. So at 30 degrees Celsius, the partial pressure of water vapor at saturated condition is 4.2431 kilopascal. Similarly, at 90 degrees Celsius, the saturation partial pressure of water vapor at saturated condition is 70.114 kilopascal. And you can see the difference, 4.241 is in left side and 4.2431 is in right side. Similarly, 70.11 and 70.114. So very little difference. So for all practical purpose, the saturation pressure temperature data for pure water is considered for the analysis of water vapor present in the air also. So this figure, this phase diagram will also applicable for the study of water vapor present in the atmosphere, because the saturation pressure temperature data deviation is very less. So we will consider this saturation line, this B to C line. There are three line: AB line, BD line, BC line. So BC line is basically the saturation line of vaporization curve. So this is the BC line. Basically in the right side, this is the BC line. Okay, and in between BC line, the 0 degree Celsius is the left side temperature, and right side temperature is 50 degrees Celsius. So if we draw the horizontal line from this point C, then we will get the vapor pressure data at this. Okay, so this is about the shape of the psychometric chart. Now Asray suggests the following equation for saturation vapor pressure of water, which is valid for 0 degree Celsius to 100 degree Celsius. So saturation pressure temperature data is also related by the empirical relation provided by the Asray. So this is the saturation pressure and this is the temperature. If we put the data of temperature and the coefficient of C1, C2, C3, C4, C5, 6, and then we can easily evaluate the saturation pressure for a given temperature. So we can write that P saturation is the only function of the T saturation. The saturation pressure is the function of temperature, or temperature is the function of pressure, where T is in the Kelvin, okay, and P is in the kilopascal. So from this formula we can also develop this saturation curve B to C. So using this formula also we can develop the BC curve for a given temperature. Okay, so first is the construction of constant DBT line. First we will see the construction of constant DBT line, humidity ratio line, and PV line. So DBT in generally we indicate in the x-axis. So all the vertical lines are the constant DBT line, and we work in between 0 degree Celsius to 50 degree Celsius. So left point is 0 degree Celsius and right point is 50 degree Celsius. We will work in between this only in all the psychometric air conditioning process. Okay, similarly the humidity ratio line, so all the horizontal line, this horizontal line is the humidity ratio line, this humidity ratio line, and humidity ratio generally present in the atmosphere is in between 0 kg of water vapor to 0.036 kg of water. This is the maximum humidity. Okay, so 0 kg of water vapor is the minimum, means completely dry air, and water vapor present in the atmosphere are generally this 0.036 kg of water vapor dry air. So we draw vertical line from the 0 degree Celsius, we draw the vertical line from the 0 degree Celsius, it intersect the saturation curve. So this point is called point B. We will extend this curve up to this value 0.036. 0.036 the maximum. It means the water vapor in the atmospheric air varies in between 0.036 to 0. So this point is C. Okay, so this is the saturation vaporization curve. Saturation curve for vaporization, or we can say this is relative humidity 100% saturation line. Okay, we also know the relation between the humidity ratio and PV. Okay, so this is the relation of omega is equal to this 0.622 PV P minus PV. So omega is the function of PV, PV is the function of omega. So we can also plot PV in the y-axis. So the constant PV line will be also horizontal line. So these are the constant horizontal line, constant vapor pressure line. So these are the horizontal line. Okay, how we evaluate the zero vapor pressure? So if we put the zero omega, this is the omega zero. If we put the zero, then we can find the pb. So pb will also be zero, so it is 0 kilopascal. And if we put this value, if we put the 0.036 at this formula, then we will have the maximum vapor pressure, that is 5.543 kilopascal. So this is the maximum vapor pressure of the atmosphere. So generally the vapor pressure, partial vapor pressure varies in between 0 kilopascal to 6 kilopascal. This is the partial pressure of water vapor in the air. Okay. Next construction is the constant relative humidity line. How we draw the constant relative humidity line? So let us consider we draw the 50% relative humidity line. We will draw the 50% relative humidity line. You can see in this figure the behavior of different lines. So this is the 100% relative humidity line. Then there is 80% relative humidity, then 60%, then 40%, then 20%. And you can see these curves are not exactly parallel. This 100% RH line is saturation line. These curves are not exactly parallel in the higher temperature region like 40 degree, 30 degree. It is parallel up to some 20 degrees Celsius or 15 degrees Celsius. These lines are parallel, but beyond this, these curve are diverging. So now how we draw this relative humidity line? So 100% relative humidity line we obtain from the phase diagram. So we don't worry about this 100% relative humidity line. We can draw the remaining relative humidity line that is lower than 100%, but these are not exactly parallel in this higher temperature region like 40 degree or 50 degree or 35 degrees Celsius. So we require two intersection point to join this line. So here it is written that we need two or three intersection point to join this line. So we will consider the two temperature interval. So temperature interval between 20 degrees Celsius and 40 degrees Celsius. Okay. So consider a 20 degrees Celsius line here and 40 degrees Celsius line here. Okay. So in between these we will draw the relative humidity line. Okay. So the our objective is to draw the 50% relative humidity line. So we will put the formula RH equal to 0.5 and P water vapor, PS water vapor, that we have already defined the relative humidity at 20 degrees Celsius. So first we are considering for 24 degrees Celsius, and saturation pressure of water vapor from the steam table at 20 degrees Celsius is 2342 Newton per meter square. So from this we can get the vapor pressure of water, that is the 1171 Newton per meter square. This is the actual vapor pressure at 50% relative humidity. Then humidity ratio we can calculate 0.622 pwb 101,325 minus 1171. This is the barometric pressure. So we are considering the barometric pressure is standard barometric pressure. Then we the value obtained is 0.00727 kilogram of water vapor kg of dry air. Okay. So now we have one intersection point. Okay, that is, suppose we are considering the psychrometric chart again. So this is the psychrometric chart, and we are considering the 50% relative humidity line. So this is 100% RH line, and we are considering 20 degrees Celsius. This is the 20 degrees Celsius line, and we have the humidity ratio value that we obtain is 0.00727. Okay, so we will represent this 0.027 here. So consider this point is 0.0027. So draw the horizontal line, constant humidity line. This is the omega is equal to 0.00727 kilogram of water vapor kg of dry air. Okay, so this is the one intersection point. This is point 1. Now we require another intersection point that we are considering at 40 degrees Celsius. So suppose we are considering, we draw the vertical line 40 degrees Celsius. Okay, so now we will calculate the omega for 40 degrees Celsius. So similar calculation we will perform at 40 degrees Celsius. Again RH equal to P water vapor, P saturation water vapor, but at 40 degrees Celsius. Is from steam table the saturation pressure at 40 degrees Celsius is 0.073 bar. So vapor pressure is 0.03685 bar. So humidity ratio at 40 degrees Celsius will be, if we put this value, we will get 0.02348 kilogram of water vapor per kg of dry air. Okay, so now we will denote this in the y-axis, considering this is, for example, this is point like this. So this point, this is, for example, omega is equal to 0.02348 kilogram of water vapor per kg dry air. So this is the another intersection point we will get. So this is the 2 point. So we will connect this 2.1 to like curvature. So by hand we are connecting these two lines. So this is relative humidity equal to 50% line. Similarly, also at any other temperature we can get third intersection point also, then we can connect this line also. Okay, so similar way we can draw the different relative humidity line like 20% relative humidity line, or we can draw 90% relative humidity line. So these are the construction of relative humidity lines. Okay, next construction is the construction of specific volume lines. How we construct the specific volume line? So you can see the nature of the specific volume line. This is the inclined line. These lines are the constant specific volume line. The units are meter cube per kg of dry air. So how we draw this constant specific volume line? So let us consider the 0.85 meter cube per kg of dry air. So this is the specific volume of moist air. We are considering 0.85 meter cube per kg of dry air. And we have already studied in the previous class, the specific volume of dry air is equal to specific volume of moist air is equal to specific volume of water vapor. So all the volumes are based on the per unit mass of dry air. Okay, so all volumes are equal. Okay, so again we require the two intersection points like previous relative humidity case. So first intersection point we consider 20 degrees Celsius at saturation curve. So now we are considering at saturation curve means 100% RH line. So we are considering 100% RH line and 20 degrees Celsius line. Okay, so suppose I am again drawing this uh, line. So consider a chart of psychometric chart, and this is psychometric chart, sorry, this is straight vertical line. So this is the, so 20 degrees Celsius we will consider. So this is the 20 degrees Celsius line, vertical line, and it will intersect this point RH 100%. So this is the first intersection point. This is the first intersection point. We require the second point. First point we have 20 degrees Celsius and saturation line. Okay, so 20 degrees Celsius at saturation curve is the first point, first intersection point. Here it is written that first. Okay, now we'll determine the humidity ratio. Okay, so specific volume we are considering 0.85. This is specific volume of moist air, or specific volume of our dry air, or specific volume of water vapor. So from the ideal gas equation we can find the specific volume of dry air is the specific gas constant for air is 287.3, and this is the temperature, and this is the barometric pressure, and 2342 is the saturation pressure at 20 degrees Celsius. So this is 0.85 that we are drawing 0.85. Okay, now we are finding the omega saturation. This is saturation curve. So basically this is the humidity ratio at saturation curve. S indicates for the humidity ratio of saturation. So at 20 degrees Celsius we again apply the same formula. The saturation pressure is same. So humidity ratio is 0.01472. So we again draw this kg of water vapor kg of dry. Okay, now say at 25 degrees Celsius. Now we are considering to determine the second intersection point. We are considering the 25 degrees Celsius line. So we again draw the vertical line of 25 degrees Celsius line. So this is the 25 degrees Celsius line. Now we require the intersection point. So we need to determine the again omega. Okay, so at 25 degrees Celsius we will again find the omega. Now first we find the partial pressure of dry air at 25 degrees Celsius. So if we find the partial pressure of dry air at 25 degrees Celsius, then again we apply the ideal gas. Here the R is the characteristic gas constant for air, which is about 287.3 kilojoule per kg Kelvin, and this is the specific volume of dry air. So partial pressure of dry air is 1,00724 Newton per meter square, and total pressure is the constant which is fixed for a particular location. So that is 101.325 kilopascal. So from this we can find the partial pressure of water vapor, which is equal to 601 Newton per meter square. So this is the partial pressure of water vapor. Okay. Now from the expression of humidity ratio, we can put this value 605 here. Here we can obtain the humidity ratio, that is 0.0597 kg of water vapor per kg of dry air. Now we will draw this horizontal line 0.0597. For example, this point is this point, so like this is the omega equal to 0.00597 kilogram of water vapor kilogram of dry air. So now we have the second intersection point, this 1 to 2. So we require two intersection point to draw the constant specific volume line. Now we will connect this 1 to 2. So now we will connect this 1 to 2. So this is the specific volume line. Okay, straight line 1 to 2. So by similar way we can draw the constant specific volume line parallel to this. Just this is like a straight line. So in this way we can draw the constant specific volume lines for other condition also. Okay. Next is the how to evaluate the dew point temperature from psychrometric chart. Okay. So how we determine the dew point temperature for given condition of moist air, we will see here. So the question is determine the dew point temperature of moist air at 25 degrees Celsius and 50% RH. So for example, we have given air of 25 degrees Celsius and 50% RH. Okay, then what is the dew point temperature? This we will determine. Okay, so how we determine dew point temperature? Move along constant humidity or vapor pressure line up to saturation curve from a given state of moist air. So from given state of moist air, we will move along this constant humidity line. So first we will denote this 25 degrees Celsius and 50% RH in psychrometric chart. So we will denote this. So we find the 25 degrees Celsius. It is written that this is the 25 degrees Celsius line. So draw the vertical line 25 degrees Celsius line. So this is 25 degrees Celsius line, and this 25 degrees Celsius line intersect the 50% relative humidity line. So this is 50%. So we draw the 50% relative humidity line. So given state, so this is the state. So this is one. So this is the given state of moist air. Now we will move along the constant humidity line. Okay, so we will move constant humidity. Okay, so this is the horizontal line, constant humidity line. We will move along the constant humidity line up to saturation point. So this is the saturation point, this point is the saturation point, and it draw the vertical line at this. So this is the dew point temperature. which is 14 degree Celsius. So this is the dew point temperature for a given condition. So this one is given 25 degrees Celsius, this is 25, this is 50, intersection is 1. Now from 1 move along the horizontal line. Horizontal line means along the constant humidity line up to saturation curve. So this is 1 2. Now from saturation curve go vertically down and you see the scale given in the dBT axis. So we find the dew point temperature from the scale of dBT only. So this is 15, so this will be 14 degrees Celsius. So the dew point temperature for this air, this is the dew point temperature for moist air, moist air of 25 degrees Celsius and 50% relative humidity. So we can also verify this from this TS diagram. So we are moving along the constant vapor pressure line, so this point is 1. So we are cooling the air at constant pressure line like this. It intersect this saturation curve, this is saturation curve, this point is dpt. So this is the dew point temperature. Okay, so how we evaluate the dew point temperature, that we have seen. So for this lecture, this is only about the relative humidity line, specific volume line, dBT lines, and constant humidity line. In next lecture we will study about how to draw the constant wet bulb temperature line and constant enthalpy line. Okay, thank you.